to Embedded Internals. This is 10th episode of our series Execution Awareness series. In this episode, we are going to debug or we can say observe our program like an Linux engineer. From a programmer point of view, debugging is the most difficult task one face. It's easy to write the code, do the logic, but once our program got stuck anywhere, debugging it, rectifying the error and moving forward, or debugging it in the production environment, debugging it when we have a large code base is a challenge. Most of the software industry is based on debugging. Most of the time, engineer spends his time on debugging the code. So, this is going to be a very important episode from developer's perspective. Have learned everything from from writing the source code to what is inside the ELF to how the compile, what is process, memory, system calls, and how the dynamic linking of the library is done. Now it's time to see what happens when the program is actually not working as per expectations. So we have some observation toolkit, or we can say some commands to observe the program. Let's start. Let me first explain you the commands, then we will move to uh, Linux operating system for the execution of all those and see. These are the most important commands. We have lots of other commands as well, which we have used in the previous episodes, and we will use in this episode as well. So strace is to trace the system calls. So it is at the kernel interaction level, how our program is interacting with the kernel. ltrace is to trace the library calls. GDB to trace the our executions, program execution step by step. Proc to live process internals. Whenever our program or process is live, we can check whatever resources or internally how the program is behaving. So proc gives the live process internals. For memory layout, we can use pmap, top, htop, all these four uh, resource uses. So when we say strace can be used to check the system calls. We already wrote. System call can include any file operations, memory system call, process creations, or we can say any kind of error. Everything can be checked at the by using syscall. ltrace can be used to trace the library calls. So step one by one, let's first run these commands and then we will go through each command to understand what actually these are doing. Okay, so let's move. I will show you the code once. This is our code to print a statement, which is to print hello world, welcome to embedded internals on our screen. Okay, we have used a printf statement, so we have used corresponding header file stdio.h. Okay, let us trace the system call. Let us first compile it. Gcc hello world.c. If we know, we get the executable. Let me trace the ELF. strace is used for syscall tracing. Okay, this output you will get. So first system call you are saying is execv. It is taking this your ELF as a process then brk, mmap, access has been provided, open at, all the system calls whichever been used you can see there, fstat, mmap, close, read data, pread, arc, prctl to set the architecture, tid address, r sequence, m protect, pr limit, unmap, fstat, all the system calls are code are this elf is using. And finally the write system call, which is correspond to printf library function. So likewise we have checked the system calls which are being used in the in our elf. We can also trace the library functions our elf is using. So ltrace hello world dot c, sorry, hello world. Oh, you have to use dot slash hello world. So the library call corresponding to write system call is puts. So it is, see, the both two statement are same, but it is in strace, it is in ltrace. Ltrace means these are library calls, whereas this is system call. In the episode where we have described user space versus kernel space, we have detailed discussion about how the library functions get converted into system calls, how system call move back to the user space, or system call is basically the part of kernel, whereas library calls are the part of user space. So we can say by strace we can actually tracing the syscalls, whereas by ltrace we are tracing the live calls. Okay, uh, like this. When you say strace or your elf file, this will trace syscalls used by the, this is in kernel space or kernel interaction, whereas ltrace dot slash elf is to trace the lib calls, which is part of user space or glibc library, shared library. So we can say that both uh, strace and ltrace are used to check the full stack of the kernel from user to kernel space. Now the third part is GDB. Like GDB, you can run dot slash, oh sorry, let us first write start I to get the start execution. So our program gets started from underscore start, not from main, which is supplied by this library. Okay, so we can by using the GDB, which is used for debugging, we can break. Let us add some break commands. Break at main function. Okay, break at printf. So R is for run, or you can use run. You have added main, break at main, so it function got stopped at main. Now continue, see to continue. When you continue, you will see you get the statement whatever you are running. We can check in the by using GDB addresses or CPU registers, stacks, memory segments, instruction flow. In the advanced code, we can check everything by using the GDB. GDB is like walk into the execution. So GDB is used for uh, Walk inside execution, we can say. From GDB, we can get registers, stacks, memory, etc. etc. Now comes the proc. Slash proc. Proc is for live debugging, okay? Slash proc means live debugging. Live process debugging, so process should be running when we are seeing the proc. Okay, then only we can see. We need the file descriptor to check the proc statements. So let us initialize underscore proc slash proc. Okay, I am doing some code changes to check the proc, because we need the program to be running for the to live inspect it. So I am using some sleep, so that program will be stuck at this level, will go into the sleep state till the time we can check all the details of this program. Okay, so let us compile this and then run dot slash. Now the program is running. In the process table ps-ef, check the PID of your process. So our process is this, and corresponding PID is 1065. Let's move to proc 1065. Okay, what can we check? We can check the status. I think our code is sleeping, so its state is sleeping, name is this, process ID is this, parent process ID is this, file size, group size, all these things, k thread, memory it is taking, everything, every this process state, detail of this process is in the stat table. If you see in this process, okay, I think process done execution. Let us increase the sleep time so that we got more time. 150, or let me do some more, 300. Compile the code and then run it. As new process has been created, new PID will be generated. So PID this time is 1076. So let's move to 1076. Let's move to this directory. Corresponding to this PS, we have lots of files. Each file contains its status. Syscall has system calls, status, statem, state, M is for memory, stack information, S maps, session IDs. These all maps, memory. So every detail we require corresponding to this process is available inside slash proc directory. Let us see some of the files. Like status, we have already checked. It's giving sleep, process IDs, parent process IDs, all the information of memory and all these information. Similarly, we can get file descriptor if there is any corresponding. So file descriptor itself. Let us go to FD 012. Three corresponding file. These three are by default file descriptor corresponding to read, write, and error. Cat mem will give the memory information. Okay. Maps is giving the memory information. So our stack memory range corresponding to this, and this is the stack memory range. With its permission is read, write, and executable permission. Come similarly to stack, we have heap segment here. heap, we can see the corresponding memory address of the heap segment. So like this, we can see the um, memory memory addresses of the particular segments or memory, whatever memory it is being mapped at. Let's see what is inside syscalls. Okay, address corresponding to system calls. So any information you need is available inside the slash proc directory for the running program. Okay, so you can check only when it is running, otherwise information inside it. Okay, every environment variable whatever is used in this is available in this file. So like this, so we can say it, and as the code is still running, you can see the process is available inside process table. Once it will program will execute, finish execution, process uh, is will be removed from the process table. Slash proc is used for live process internals or live process debugging. We can debug process information, CPUs, process info, like we have check status file, CPU info and everything, mem info, like we have checked maps which contain the memory map, and similarly all other file corresponding to some or the other detail of the process. So we can say that under slash proc is a real time window into the kernel. We already have checked the pmap. Let me show you once again. Sorry. Pmap corresponding to 1076. This is the memory mapping. Memory address correspond to libraries, ELF, stack segment, its size and permissions. So these all are the memory details which are being used by the program is available in pmaps. So pmap will show the memory region. This is the region. It is also showing the libraries and the corresponding size of everything. Similar way we can see by using top what all are the resources is being used by this. Top is giving the virtual address, res, CPU, how much CPU it is taking, how much memory it is taking. So let's see where our program is. Our program is actually in the sleeping state right now. No memory and no CPU because our program is currently in sleep state. And the PID corresponding to this is 1108. PR is purity, virtual address, resistance, SHR. All these are information available. We can also use htop to check the resources. These all are the process. This is our hello world.c. It's also says the state, so state sleeping. So like this we can use htop and top to check the CPU usage, memory usage, all the running processes. This is CPU uses, memory uses, running processes, time it is all the processes taking, the corresponding PID who have initialized who run those program, its corresponding priorities, and the memory information, which is very useful for while we are debugging any program which is in the performance stage, performance debugging, or the production environment. We can debug the program using these tools very efficiently. So at this point of time, we have checked everything. You have debugged using strace. So any point of time you need to check whatever system calls, whatever kernel is doing, you can use these commands. And to debug a program like a pro, you can use all these commands. And apart from that, we have other commands as well, like read elf to understand and debug the elf executables, nm object dump. But those are to debug at the code level, but these are to debug at the program whole program level. You can also check the corresponding memories which are being linked, corresponding libraries by using LDD. Sorry. Still running. Whatever the library it is linked with, linker loaders, all the information will be available here. So one master point uh, is that whenever we are observing or debugging any code, we should always move from outside to inside of it. Like from first step is to debug our code, then to move from libraries, then to system calls, then to like this. It will be easy to pinpoint exact location where the problem is actually occurring. So let me show you the observation. Like we have observation tool, we can use some flow while observing or while debugging any code. So I can say this as observation flow. Observation flow. We are moving from outside to inside. So outside means from user space to kernel space. So first step to run the program. If there is any compilation or some error, you will get at that compilation stages or something. Once the program is running, you can trace the system calls using strace. This is to trace the syscalls. You can then trace the library calls. Then you can use GDB for instruction level debugging. /proc, once the program got live, you can use this /proc live debugging, or we can say runtime debugging. And pmap or other tools for memory layout. Htop for C for resource information. By using all these things, you can debug a code like a pro, like an engineer. This is last episode of our execution awareness series. If you have followed this series from the first episode till today, I at this point of time I understood that you must have understood compilation pipelines, ELF internals, process creations, memory layout, system calls, dynamic linking, and also you are able to debug a program like a pro. If you have any question, any suggestion, or any topic you can suggest to, or any feedback, please write down in the comment section. Thank you. Thank you